Okay, hello everyone. My name is Christian Hom. I'm a second-year PhD student at Temple University, and I wrote this paper with Boyang Zhu and Dr. Pei Wang. And so today I'm going to be talking to you about goal generation and management in NARS, which I'm sure many of you are familiar with. So, what is a goal in general? It's a motivation for a cognitive system's activities. So a goal is meant to drive your system's actions. And goals can take many levels or any level of complexity, specificity, and content. So a specific goal might be something like pick up that red apple on that table. And a more general goal might be you telling your robot to be good while you're gone. Goals can be distinguished between actively pursued, or latently desired. And to achieve goals, you need to use context, which is what you believe is true in the current moment, and also knowledge, which is what you think is true in general. What systems have goals? Every computer program has at least one goal, and that's the whole point. You can consider a computer program or just a simple algorithm's singular goal to be to reach the final state of the algorithm. Automated systems might have a couple of goals, or maybe one or two. So take, for example, this stimulus response robot, which I found online. It has one goal, which is to pick up paper cups out of the line. The context or stimulus is just a paper cup detection. And the action the robot takes is to move and pick up the paper cup. Systems that can only handle a couple of goals are very highly specialized and will be fragile in general context. I think that's pretty obvious. And if their program goal can't be immediately achieved, these systems will die or fail or simply idle until the stimulus comes. So now we'll talk about goals in AI. They can be either input by an external source like your user or derived by the system itself. And this is where we talk about goal derivation. So essentially when a system can't achieve its goal immediately, it'll use knowledge with backward chaining to derive new goals, whose achieving either implies or equates to the original goal's achieving. And this is a recursive process. So every sub-goal that you derive might require further sub-goaling. And if you look on the right, you can see that the goal derivation process can be viewed as a tree where your input goal is at the root. So here, if you can read that, the root goal is to close the door, and you might derive another goal such as stand near the door and push the doorknob and so on. And then we can view all possible goal derivation paths in the system as a forest of goal derivation trees, where the number of the trees in the forest is equal to the number of distinct input goals. And you'll notice that goal derivation trees will bottom out at their leaves, which are simply goals that are either atomic actions that the system can execute immediately, so there's no need to derive anything else. Goals that are already achieved, again, no need to derive anything. And finally, goals that cannot be further sub-goaled due to the system's insufficient knowledge. And in traditional AI, systems might be programmed to pursue predetermined final goals or super goals, which people tend to talk about, and hierarchically manages these derived goals and try to maybe achieve the sub goals before traversing up or working towards its final goal. And the system may distinguish between separate goal planning and action phases, where it takes actions to pursue its goals. But in AGI, goals should not be ordered or managed hierarchically like this, and we'll talk about that why. However, we can still analyze goal derivation paths graphically using these trees, although the branches and nodes are constantly changing. And that brings us to goals in AGI. So AGI focuses on general purpose systems with regards to cognition and problem solving across domains. And that introduces a few requirements for AGI system designers. Primarily being that it needs to work under an assumption of insufficient knowledge and resources, as specifically two principles of being open and working in real time. And in terms of goals, this means the system needs to be able to accept and pursue arbitrary goals, and that means a goal with any content, as long as it can be expressed to the system. And it also needs to manage all of its different goals at runtime without any change in, without any delay or extra time. Otherwise, if your system does not meet these requirements, the AI is restricted to a specific domain or task, and you can't consider it general purpose. And so regardless of whether the goals are input or derived, we treat them independently and not as a necessary or sufficient condition for another goal. An AGI system, therefore, doesn't have super level or super goals, final goals, or top level goals that it focuses on, even though people assume these exist, because the designer can't hard code what the system goals are going to be or what it needs to focus on in its environment. Instead, the system autonomously learns and pursues its goals, which are changing constantly in terms of desirability, priority, and personal meaning to the system from moment to moment as the system reasons and interacts with the world in real time. And instead, like I said, instead of focusing on achieving a final goal, the system adaptively manages its entire goal complex holistically to achieve all of its goals to the best extent. And it does this by giving a probabilistic share of processing time to all of its goals and treating them independently based on the derived evidence. And so you'll notice over here, this is an example of a NARS goal complex. These are all separate goals and none of them are dependent on each other. They're all stored and treated independently. So I'll quickly give a NARS overview. I don't know if everyone's familiar with it. NARS is an AI system designed in a reasoning framework, and the system has a memory filled with concepts and performs reasoning. The format of the system is defined by a formal grammar called NARS, which is processed using its corresponding logic. It's called non-axiomatic logic, or NOW. And the system constantly is processing sentences of NARS, which carry information and knowledge. And the logic is intrinsically designed to help the system learn and use uncertain and conflicting knowledge. And critically, the logic of NARS and the system design are specified under ICER, which I talked about earlier, which means it has a finite processing capacity. It doesn't need additional computational resources. It works in real time, and it's open to tasks of arbitrary content. And you can read Dr. Pei Wang's non-axiomatic logic book, which is a fantastic book. And if you're interested in that, I highly recommend to read this. So we'll talk about a judgment in NARS, which is a type of sentence with this grammatical structure. And a judgment, basically it's a sentence that describes a piece of knowledge or information, and it can have a tense, like this happened in the past, present, or future, or will happen in the future, and it has this period as punctuation. That's how you identify it as a judgment. It contains a statement which has a subject, predicate, and a connector or a copula. And so, for example, this is a NARS judgment that says dog is an animal. The truth value at the end is a pair of numbers, frequency and confidence, that summarize the judgment's evidence for and against the statement. So the frequency represents the ratio of positive evidence to total evidence. Basically, how true is this statement? The confidence represents, the confidence of the frequency as based on the total evidence. And every concept in NARS, because NARS stores concepts in its memory, contains a data structure called a belief table, and it stores these judgments. So we'll quickly go through a NARS lifecycle. So when a NARS instance is created, a new one, its memory starts out empty. And the system accepts inputs anytime, putting them in these containers called tasks. And it processes these tasks. And when processing them, it conceptualizes and integrates them into the system's memory. So for example, we may have statements, raven is bird and a bird is an animal. That's what it looks like in the memory. Then the system will continuously do inference, and this is how it learns, plans, and makes predictions. This is how the system operates. It continuously does inference. So here, using the deduction rule, the system will derive that a raven is a type of animal as well. Now we'll move on to goals. In NARS, this is a goal is a type of sentence, like a judgment, with this grammatical structure. And it contains an event named by the statement that the system desires to make true. Has an exclamation point as punctuation. That's how you can identify. And the desire value is, again, another pair of numbers, frequency and confidence, that summarize the evidence for and against the event's desirability. So the frequency represents how desirable is this event, and confidence represents the confidence and frequency. There are two types of goals that we can represent in NARS, positive and negative. A positive goal is simply a goal with a positive statement, like I want the door to be open, is what this goal says. Negative goal is the same thing, but it's a goal with a negation statement. So I want the door to not be closed. And both of these goals will cause NARS to try things to open the door, although we prefer the positive goals because they're syntactically simpler. And just like every concept has a beliefs table, it also has a desires table. So every concept will store beliefs about the concept as well as desires about the concept. And that's how the system keeps track. And goal is unique to the logic. It's meant to provide motivational mechanism in NARS. But we don't have to do anything special per se. We don't need to redefine the logic or implement any special rules. Instead, all we do is we combine and extend the lower levels of the logic, now 1 through 7, to define now 8, which is the goal. So first, we just define a virtual event, we'll call it D, representing the system's overall desired state. The event is virtual, which means that this event D doesn't exist anywhere in NARS in the system. It's theoretical. It's a non-existent state that the system constantly strives towards. Then we simply define goal as a higher order judgment. So a goal S with a desire value here is equivalent to this judgment on the right with the same truth value as the goal's desire value, where D is NAR's overall desired state. And basically what this is saying is the event implies NAR's desired state. And then we can treat goals as in inference as judgments with no special changes to logic. So here's an example of that. So in NARS, if we had two judgments, P implies S and S, we can use the conditional abduction rule to derive P, like that. If the two sentences are a judgment and a goal, we don't treat it as a single statement. Instead, we treat it as a higher order statement that we just discussed. And these premises conform to a different inference rule, which is the deduction rule. So P implies S, S implies D, and by deduction, P implies D, which is equivalent to the goal P exclamation point. So goal processing has two unique stages in NARS. First is the initial processing, which is when the goal task is processed from the buffer and it's integrated into the system's memory. And then we have continued processing, which is when the system performs reasoning on the goal with related concepts. So we'll run through some visualizations quickly. First, a task containing the goal enters the buffer. Then the system will select the task for the first time, and this is when initial processing happens. So the concept for the goal is activated and accessed. Then the content of the goal is merged into the concept's desire table, which keeps the event's desirability up to date. And then the system moves on to the next task. That's initial processing. At another time, the system will select a concept from memory probabilistically, and then the goal will be selected from the desire table for processing. The continued processing starts by calculating the desirability of the goal using this equation here. It's an estimation of the future frequency. And then it applies the decision-making rule, which means to pursue the goal only if the desirability is higher than some threshold decided by the system designer. And that threshold represents NAR's cautiousness. So the lower the threshold, the more goals the system will pursue. The higher the threshold, the more desirable the goal has to be before it's pursued. Then we check if the goal is true, and if it is, well, we can stop. If it still needs to be made true and NARS needs to achieve it, if it's an operation, we execute it immediately. So something like jump or run, the system can just go ahead and do that if that's desired. But if it's not an operation, we need to select a semantically related concept from the memory and then continue on. And that's what's happening over here. And then we select a belief from that concept, bring them together for inference, and derive a new goal, which is added to the buffer. First, we'll talk about functional autonomy in NARS. So essentially, an important feature of NARS is that the motivations that are derived for one reason or another take on an independence or a life of their own as the system continues to experience new things in response to the system's changing knowledge and memory structure. And we see various examples of this in human motivation. So this will be kind of a silly example, but as a child, you might have had a goal to make your parents happy, and they'll praise you. So then you enroll in a kindergarten or school and your parents say, well, you need to do your math homework and we'll be happy. So you might derive a goal from this, G prime, to do your math homework because that will help make your parents happy. Then as you get older, you might develop other interests like, you just want to get good grades and you also want to play video games. So you learn how finishing your math homework will lead to these things. If I do my math homework, I can play video games. If I do my math homework, I'll get an A. You also might derive more evidence using these relationships. Then as you get older, you may outgrow your need for parental praise. And you also might want to do your math homework due to the other relationships and derivations that are occurring. So some of your motivation is lost here. And then once you graduate, these conceptual relations may no longer even be relevant to you or desired, and you may no longer care to do math homework. And this part of the network motivations become basically inactive. And this is all to show that the goal G prime, the derived goals are not strictly restricted to sub-goal of any of these other goals. It's accumulated evidence inferred from the system's many goals and conceptual connections. And the system's conceptual relations are constantly reorganizing and changing in meaning. So here I'm going to show a couple of working examples in virtual environments using open NARS for applications. The system was introduced last year at AGI-21, and it's an open source project available here. Yep, that's all it'll take. So here we have an example of an obstacle course, and this is an example of NARS doing goal derivation. And hopefully it doesn't blank out while the movie plays. And here the system has a simple goal, which is to touch the finish line. And it's given a little bit of background knowledge about how it can interact with the world. And here we can see the system, well, now we can see the system in real time deriving goals to jump over these obstacles when it encounters it to touch the finish line. And I won't go too deep into the technical specifics of this, but if you're interested, you can review the slides after. Here's the background knowledge that was used. We have 2 pieces of background knowledge and only 1 seed goal. And using these beliefs and seed goal, the system will derive new goals using deduction. It'll see an event, something like the path is clear right now, derives evidence to walk forward. And then it might see context evidence that the path is now obstructed, and it'll derive evidence to jump. And that's how it jumps over these obstacles. Here's another example, which is a NARS car. In this example, we have 2 seed goals because this is an example of conflicting goals, which is we want the car to be en route to its destination with a lower desirability. Then we want the system to not hit pedestrians, which has a much higher desirability. So we want the car to do 2 things: to drive and don't hit pedestrians. And so we'll see what Ona does. It drives forward, and upon encountering the pedestrian, it brakes. We'll move the pedestrian out of the way, see what happens. And the system continues driving. Here's another pedestrian, and the system brakes. We'll move them out of the way. And the system continues. So here again, we have the same thing, a couple pieces of background knowledge, like if you're driving, then you're on the way. And if a pedestrian's in front of you and you brake, then you're not going to hit that pedestrian. We input the seed goals. The system derives new goals using deduction and context. You'll notice here that the system derived evidence to drive with a desirability of 0.59. Here it derives evidence to brake with a desirability of 0.63, which is a little higher. Normally, since we treat goals independently, this doesn't matter because both of the goals pass the decision-making rule. So when we select both of these goals for processing, they both pass the rule, so we're going to process both of them, no problem. Operations like braking or driving are a special case though. In a given moment, you don't want to select a less desirable action. You want to choose your most confident desirable action. So in this case, because brake is of a higher desirability, it chooses to brake over drive. So in conclusion, NARS is a real-time system that can process goals of any content at any moment, and it can desire events to either occur, and those are positive goals, or be prevented, and those are negative goals. The system has many goals at once, and they can be constantly derived while the system operates. Eicher implies there is no guarantee that a given goal can be achieved, so the system never focuses on one goal or super goal or subset of final goals. Instead, it processes all of its concepts in parallel so as to try and achieve all of its goals to its best extent. The system's constantly changing conceptual knowledge and dynamic goal derivation mean the meaning of goals is never static, but it's constantly changing. For this reason, goals are treated independently based on derived evidence. Goals are active or latent depending on how often and recently the goal is derived and how strong the evidence is for the derivation. And finally, by virtue of the system's adaptive goal complex and its subjective experience, we can compare the system's psychology to a human's and say that the system can develop its own individual traits, attitudes, and interests that evolve over its lifetime.